All right, let's get started. So last time we discussed functors, which, if you recall, are the morphisms between categories in the category of categories, right? And the sort of restriction, so they map objects in one category to objects in another, and morphisms in one in this category to morphisms in another category, with the restriction that that mapping has to preserve composition. So we're going to look at a few more examples of functors today, because last time we sort of really focused on the endofunctors, right, which are the functors from a category to itself, because those are a little bit easier to grasp if you're a programmer. It's just a matter of higher order functions, right? Like, so the fmap function, remember, that's takes some function and maps and converts it to a function between the types of the functor. All right, so that's a little bit easier to understand if you're a programmer. But we're going to look at some functors between categories that are not the same today. So if you recall from last time, we looked at the functor which took an object there and mapped it. So we fixed an object in our category, and we take this functor, maps any object to that object's product with A. That's a functor from C to C. Now, of course, because we've seen that the product is isomorphic to the same product with the objects reversed, we have another functor. Basically behaves exactly the same way. It behaves exactly as you'd expect. So that's good. These are pretty easy to understand. But unfortunately, we can't, using just endofunctors, we can't actually map to any arbitrary product. We have to have it fixed like that, right? And the reason for that is because, you would actually have to have a functor with two arguments in a way, right? So it takes two objects and maps them to the product, and it takes two morphisms and maps them to the product morphism. So you can't really do that with endofunctors, but if you recall, we had a construction on categories called the product category, which had as its objects pairs of objects in each of the two categories, and as morphisms, pairs of morphisms that matched up with the objects. So we could have a functor from the product category. I'm going to draw it out the explicit way like this. I'll just say this is equal to P for short. And this functor goes from the product of C with C to C. And this is, of course, assuming that in C we have all finite products, right? Because if we don't, then we'd have problems, wouldn't we? So we're going to require, for this functor to exist at all, we have to have all finite products. And as you might imagine, if we have, this just maps the objects as pairs as you would expect. So the fmap function for this is not a Haskell function, right? But it works as you'd expect. We looked at another functor yesterday, or last time though, which took an object and mapped it to the exponential. So it takes x and maps it to x to the a, right? And these are the set of morphisms from a to x. And this is an endofunctor. But again, in order to, if we don't want to fix the a there, you have to have two arguments. And now this functor is a little bit more interesting because let's take a look at what happens if we flip these. So suppose instead we fix the object A, and instead we map our functor maps the objects to the exponential a to the x. So it maps x to a to the x. This is again an endofunctor, but it has an interesting property. Let's try to figure out what it would map a morphism to. So I'm just going to draw a little diagram here. We have a function morphism from a to b. Call that f. And we have, so, no, I should have, I'll say it's a morphism from x to y, so that we can still use the a in that. Right, and now, if we have morphism from x to a, we want to figure out a way to map these morphisms from x to a to morphisms from y to a. But it doesn't look like you can do this from this with this diagram. There's no obvious way to compose these, is there? What's interesting about this is where we're getting to what's interesting about this functor is, let's get rid of that arrow. If we have a morphism from y to a, we can compose that with f and get a morphism from x to a. So this functor actually reverses, when it maps morphisms, it actually reverses the direction of the arrows. And we call this a contravariant functor. I'll type up the definition. And I'll just draw it out, right? So we have f from x to y. We then get right? Maybe you're thinking, you know, you're a little bit uncomfortable with this idea, but here's where we are going to introduce another one of our constructions on categories, right? If you recall, the opposite category, which is C, we write like that, is the category C, but with all the morphisms reversed. So instead of a morphism from x to y, you have a morphism from y to x, right? So a contravariant functor, instead of being a functor from C to some category D, I'm going to cross this out. So let me just get red there. So this functor is actually a functor from the opposite category of C to C. So that works. And the dual concept of contravariant functor, the functors that we're familiar with, are called covariant functors. I'll just type that out as well. Those are the functors that we're all familiar with by now. All right, so let's discuss Hom functors now. Now, if you recall, a locally small category is a category where for any two objects, the morphisms between those objects form a set. So we can sort of consider that as the sets form a category, right? So we can consider a function if we have a functor. these are going to look a lot like our functors to exponential objects, but this time they're going to. So here's a Hom functor. There's a on C. Let's fix the first argument, right? And so again, this is going to map the morphisms. It's going to map an object X to the set of morphisms from A to X. So it should behave the same way as the first exponential functor that we took a look at. It's going to be covariant, so it's going to go from C to set. And as you might imagine, it maps the morphisms the same way. If this is a set of, if we have a function x, y, so that's going to map to a function from the Hom sets. And of course, the way this works is you have a function here. You just compose it with f, and you get a function from A to y. Pretty simple, right? And as you might imagine, if we fix the second argument in our expression here instead of the first, you get a contravariant functor. Makes sense, I think. Now we're going to be taking a look. We're going to be looking a lot more closely at these next time when we discuss the Ionetal lemma. But for now, this is just an example of, an example of functors between categories that may not be the same category, right? But let's go back and for just a second. Before we discuss functor categories and natural transformations, let's take a look at this product functor P. Right? I'll just draw it again down here. So we have P C cross C, and basically we have an object in C cross C, X, Y, and it just maps to, the product of X and Y, except in C. We can think of another functor going the opposite direction, though. So if you have an object in C, you can obviously fix, we've obviously seen what happens when we fix one of the objects, but you can also just map. I'm going to draw the functor out first. This is a delta, capital delta, which the delta stands for diagonal. This is called the diagonal functor. And it goes from C to C cross C. And it maps an object X in C to the object, the diagonal. We call it the diagonal element. And a function f, we just map to, right? Okay. So there's obviously a limitation with this, which is that you can never get to an object like A times B unless A and B are literally the same object, right? You can only get to the diagonal elements. So if we want an endofunctor between these two, from C to C using the product, we can compose these. Right? So if we have P after delta, that's an endofunctor. And that maps X to the product of X with itself in C, though, this time, rather than in the product category. So that's all well and good. But I guess now would be a good time to start talking about functor categories. So I discussed, I think in the first lecture, that the category of categories is something called a two category, which basically means that the morphisms between any two objects in a two category actually form a category themselves. This means that, first of all, well, we've seen that the category of categories has an initial object, right? I'll just, oh dear, got my pen. I'll just type this stuff out. No, not an initial. We want terminal. That's a category with one element and the identity morphism. We've seen that and we also have functor categories. So and this, since we have all three of these, we know that right. But so we're going to talk about these exponentials in the category. So the functor category has as its objects functors, and as its morphisms, natural transformations. Now, a natural transformation is, we've sort of seen how morphisms are like functions in a way, except they have the additional restriction that they preserve the structure of whatever category we're working in. So in set, there's not really any structure, they're just functions, right? And this, of course, is, really narrowing down what morphisms actually are. But for the sake of your intuition, think of them as that. In the category top, right, the morphisms are continuous functions, so they sort of preserve the open sets, you can think about them that way, of the topological space. And in the category cat, the morphisms are functors, which preserve the composition of morphisms. Now, for a morphism between functors, what it sort of does is it preserves the mapping of the morphisms between the two categories. And I'm going to draw a diagram here to describe what I mean. So let's say we have two functors between arbitrary categories C and D. All right. And if we have Here's C. Have some objects, a morphism, right? I'm not going to bother drawing the circle. I've had trouble with that before. And D over here, we have the images of these two functors. So we have F All right, so a natural transformation, and we use lowercase Greek letters to denote natural transformations. So a natural transformation from F to G here is actually a family of morphisms in D, which are indexed by the object of C. So for every object in C, and there could be more than just A and B here, but we're just looking at these two for this example. For every object in C, we have a corresponding morphism in D, which goes from, so this is the A component of our natural transformation, phi A, and here's the B component. We call them the components of the natural transformation. And these morphisms make this diagram commute, essentially. So this means that phi B after f of f is equal to g of f after phi A. Okay. Now, in your homework, I assigned a couple questions which sort of had you finding these kind of morphisms. And in Haskell, the natural transformations, well, in Haskell you can have polymorphic functions, right? So if you have a type constructor, and I'm just going to give examples that are actually functors, but remember, not all type constructors in Haskell are functors. What I had you write was the safe head function, right? And that was a function from a list of A, and A is just an arbitrary type variable here, to maybe A. Now, since the list is a functor, as we've seen, and the maybe is a functor, this ends up being a natural transformation, which is convenient. Well, so essentially what that means is that if you have some function from A to B, I'll type it out in text. You have the restriction that f Now, this looks kind of weird, but this actually works because of Haskell's type inference. Essentially, this realizes that this is an fmap on the maybe type, right? So this means that you could take safehead and then apply the function, or the fmapped function to the maybe, or you could, and so the type inference system of Haskell will figure out that this is mapping, the f mapping using the fmap function for the maybe functor. And on the other side here, we essentially apply the function to all of the elements in the list and then take safe head. And that should always give us the same result, which we want, don't we? I mean, that it certainly should seem like that's how this should work. So the safe head, and also the safe index, because remember when the safe index function had the signature right? So this part here, you can think of as a function from the integers to maybe a, or you could consider it you consider this to be the composition of the reader functor with the maybe functor, right? So that is a functor. The composition of functors is a functor because it's a category, right? So it has to obey composition. So this is, in fact, another natural transformation. So that's good. I don't know if I have much else to discuss today. This is going to be a quick lecture. Okay, so I have, all right, let's just talk about a few more functors that I forgot to mention earlier in the lecture. Oh, one more thing. Let's discuss so we have this composition of the product with the delta right here, right? And since okay, let's draw this out again. C, or you can consider it an element of the functor category. Another element of this functor category is the identity morphism, or the identity functor. And since functor categories are categories, you should consider that there is the rule that they have to have identity morphisms, right? And the morphisms are natural transformations. So what might the identity morphisms be? Well, if we have right, so the identity, whoops, I wrote that wrong. The identity of f of a would be the identity natural transformation from f to f, right? The identity always commutes with any morphism going in or out of its object, so that's pretty obviously the identity natural transformation. And, you know, they're kind of trivially indexed by the objects because they're just the identities for the image of that object under the functor. But for the functor category C to the C, this is the set of functors from C to C. And so this should obviously include an identity, so the identity in the category of categories. And I'm going to write this as capital ID on C. That's another morphism. Now, if you recall, the principle of equivalence, the principle of isomorphism, states that we don't really consider objects in a category to be equal. We consider them to be equivalent if there's an isomorphism between them. Now, with locally small categories, the morphisms between objects were set, so we could consider them equal. But in the category of categories, the morphisms between objects don't form a set, they form a category. So we have to, in order to consider two functors to be equal, well, we can't. They're the objects in a category. We have to consider them equivalent if there's a natural isomorphism between them. So if we have an arbitrary functor from C to C, the law of, or we have a functor, say f from C to D, and another functor, I don't know, let's say from E. We have the requirement that there's a natural isomorphism from the composition of the identity with G to G. They're not the same functor. They're only equivalent up to natural isomorphism. And the same goes for, as I know I switched these around, but you can figure out what I mean. So these are no longer considered equal, the identity, when you compose them with the identity functor. They're only equal up to a natural isomorphism. But let's get back to talking about this guy. So this maps an object in C to its diagonal product. So it maps X to the product of X with itself. Now, there is, in fact, a natural transformation from I'm going to say this is we're going to call this natural transformation small delta for the diagonal morphism, right? And essentially this is a morphism in C, or it's a family of morphisms in C that map. So if we have, so I'll just write out the component. If we have an arbitrary element, object X in our category C, the component of this diagonal natural transformation for X is a morphism from X to X cross X. It's messy, but you get the idea. Okay, still plenty of time. And you might imagine that this would commute with the projection morphisms, right? So if you map, if you apply the diagonal, I'll just write them out. Pi 1 after right? And what else? Now, I should mention that this isn't an isomorphism, because if you reverse these, you can consider the product to be a lot bigger, right? The diagonal morphism. I'll just give an example with sets. It would map an element A to the pair A. But if there's other elements in our set X, there could be, you could have A, C, C, A, right, and so on. So if you reverse these, it's not really, you're not going to get the identity on the product anymore. But the fact of the matter is that this is a natural transformation between the identity functor and the diagonal functor. Okay, so that's another example of a natural transformation. One final thing I want to talk about is horizontal composition. Now, let's suppose we have, I'm in cat right now, category of categories. Let's suppose we have a category C, category D, and a category E. And I have a functor F here, functor G here, of course F prime. You know what? Before we talk about, let me give an example first. So I'm sort of drawing the functor category between C and D. Let's draw one more functor. And then we have some natural transformations between these. Now, because this is a category, we can compose these natural transformations, right? So we can get a natural transformation of this G, and that's H. That's a natural. So B after, or beta after alpha is a natural transformation from F to H, right? And we got that from composing natural transformation. And you might imagine that this is just the result of composing the corresponding components in the category D. And in fact, it is. But there's another way of composing natural transformations. So this is called vertical composition, right? Because it's sort of vertical direction. I mean, you could draw this anyway, but that's the convention. So when you compose two natural transformations in the same functor category as you would any morphism in any category, that's vertical composition. And this distinction between vertical and horizontal composition applies in any two categories, right? There's actually, I'll come back to what the terms are for the corresponding morphisms in an arbitrary two category, but let's talk about our third category, E, here. And I'm going to go back and erase some of these. No, I want this to be F prime. This one's F prime. We'll have this one be G, and this one be G prime. And we have a natural transformation in the functor category D to the C. Call that alpha. And another natural transformation. I'll call this one beta. Now, there's no way you can compose these in the traditional sense because they're not even in the same category. But if you think about it, you can compose morphisms, right? So you can compose, so G after F is a morphism from C to E, and G prime after F prime is a morphism from C to E. Now, is there a corresponding natural transformation between these? Well, there's actually several. Well, there's one. There's lots of ways to compose these four functors, but with the way that we've composed them here, there's a natural transformation from G after F to G prime after F prime, which is the horizontal composition, which I write as a star, chat's getting in the way. So that's horizontal composition. And I think that's it for today. I'll open up questions real quick. Hey, Andy.
Yeah, I was just wondering, you mentioned earlier about natural isomorphisms. I'm familiar with natural transformations, but what's the distinction for a natural isomorphism?
A natural isomorphism is it's a natural transformation that's an isomorphism, right? So if you recall, the natural transformations are actually morphisms, or the family of morphisms in the codomain category, right? So if all of those corresponding morphisms are isomorphisms, then you call it a natural isomorphism.
Cool.
All right. Any other questions? Oh, I forgot to actually discuss the terms for two categories. I don't know if we're really going to be discussing higher categories too much, but so in the category cat, you have the functors, which are the actual morphisms between objects, and then the natural transformations, which are morphisms between functors. The corresponding terms for these in an arbitrary two category so the zero cells are objects. That's what we call them. The one cells are your typical. The one cells are actually the sets, or they're the categories of morphisms between objects. So and then the two cells, as you might imagine, are the morphisms. Okay, so like in our category of categories, the one cells, in the zero cells would be our categories. The one cells would be our functor categories, and the two cells are our natural transformations. So for any two category, you have the corresponding concepts of vertical and horizontal composition between two cells, which it works exactly the same way as it does in the category of categories, except now we've abstracted away even further from what the morphisms are, or one cell or two cells actually are in this case. The two cells could be anything. They don't have to be morphisms in some category. The one cells don't have to be functors or whatnot. But I just thought I'd point out that a lot of the concepts that exist in the category of categories that we're going to be discussing quite a lot do apply to an arbitrary two category. So that's it for today. It's a short lecture. As usual, the homework, well, not as usual, but the homework's going to be posted tomorrow, as well as the solutions from last week's homework. And, next time we're going to be discussing the Yoneda lemma. So I'll see you all then. Thanks for coming, everyone.